principle, already on their own, there's not only language, but also quite nice tools that allow to prove some theorems on themselves. But now, if we enrich these tools by something very, very strong, as how we have seen, that if we add to the height machine and to the covering techniques, if we add also, say, Roth theorem, we obtain theorem of Siegel very quickly, right? So we obtain something very non-trivial. Now today, instead of Roth, we will use Baker. Baker's inequality. And we will see that, again, one can obtain some non-trivial results. And this time, since Baker's inequality is effective, the results will be effective. Yeah. But of course, they will be weaker than what one can obtain with Roth. For instance, there is still no effective version, complete effective version of Siegel's theorem. Good. First of all, let me, so today is, well, we can call Baker's method in Diophantine. So we already saw one application of Baker's method. It's how one treats two equations with Baker's method. And what I'm going to do today will be a kind of generalization of this. So 2a will be some special case of a theorem I'm going to prove today. And we will see that many other results are also special cases of this theorem or easy consequences of this theorem. So first of all, let me restate, so let me recall Baker's inequality. So let gamma 1, gamma r be non-zero algebraic numbers. Let V be a place of Q bar. Then if gamma 1 and let B1, sorry, Br be integers with capital B is the maximum of now theorem, which is initially due to Baker, but then, as I said, was refined by many, many people, and now exists in a form I'm going to display. If gamma 1 B1, gamma r Br, there's the product, is distinct from 1, then the difference Vedic is bounded by E2 minus some constant times log B, where the constant depends effectively of our data, gamma 1, gamma r, and the absolute value V. It's log B, it is the most modern form, but actually, as I already said, any function here growing slower than linear would do for most of applications. So let me first of all restate this theorem to bring it to a form which is more convenient for using in Diophantine geometry, at least in theoretical Diophantine geometry, Diophantine analysis. So now let gamma be a finitely generated. Gamma is not a good notation because I will later Okay, good. I will use gamma, but later I will use, I will speak on modular curves, and there will be another gamma which has nothing to do with this gamma. Good. So gamma finitely generated, multiplicative subgroup of algebraic numbers. Multiplicative subgroup of, well, since it is subgroup of this, then I don't need the word multiplicative. So subgroup. Good. Then, and V, again, absolute value. Then for any gamma in gamma, distant from 1, we have V is E2 minus constant log H prime of gamma, where H prime is just slightly corrected height. Say, and some number like, well, 2. Good. It's just to avoid some stupid technicalities. And C is an effective constant depending on gamma and V. What do we mean by effective constant depending on gamma? It means that we can calculate it in terms of some finite system of generators of gamma and absolute value V. For the proof, it's sufficient to establish that if we have gamma 1, gamma r multiplicatively independent, and gamma is their multiplicative combination, then height of gamma is of same order of magnitude as B, number B defined by this, where this constants involved by this order of magnitude are effective and depends on only what this gamma 1, gamma r. Good. Well, so we should show that this is bounded in terms of B, and then B is bounded in terms of this, right? So in one direction it is trivial, so we have it's trivial. It is just such that H of gamma is bounded by just by the properties of heights B1, H of gamma 1 plus etc. plus BR, H of gamma R, and then bounded by some constant times B, where the constant just maximum of the height, so it's very easy. Well, in the other direction, this is basically Dirichlet's argument used for an easy part of Dirichlet unit theorem. So we do the following. We let S be the set of all. So we let's say K be a number field containing all these guys. And we let S be the set of all places of K for which sum of lambda I is, so which are non-trivial on the group generated by these guys, for which there exists lambda I with lambda IV, sorry, lambda IV is not 1. So all the absolute values involved. So as some finite set of places. And then we consider matrix take the matrix log gamma IV, where I and V in S, it is what is R by cardinality of S matrix. And I claim that the rank of this matrix is exactly R, which is pretty clear. Why? Because the rank is R. Because if the rank is strictly smaller than R, then the rows of this matrix, what? They generate some vector space of dimension strictly smaller than R. And in this vector space, we have R Z-independent vectors, because these vectors are Z-independent. But when we have in a vector space Z-independent vectors, and the number of vectors is bigger than dimension, then they generate a subgroup which is not discrete. They cannot generate a discrete subgroup. And this means that the subgroup has elements which can be as small as possible. And so this would imply that, well, look how we define the set S. If we have gamma in the group generated by gamma 1, gamma R, then the height of gamma we can use only absolute values from S. Only absolute values from S are involved, right? And this means that we can find here in this group element of arbitrarily small height. So if rank smaller than 1, smaller than R, then group contains elements of arbitrarily small height, small non-zero height. And this contradicts Kronecker's theorem that if we take in numbers of bounded degree, then height is either 0 or is separated from 0. Contradicting Kronecker. And now we just take V1, select V1, VR, and S such that the matrix log gamma I Vj is is R by R and non-degenerate. And what we obtain the following, that BR, B1, BR multiplied by this matrix is what? It will be simply log gamma V1 log gamma VR, which is system, non-degenerate system of linear equations. And so now we resolve resolving in P1 BR, we bound them in terms of gamma Vg. These numbers. Good. It's basically the same argument we already used in the theorem when we bounded B. The proof bounded B in terms of the conjugates. We again took all the conjugates. So in this case, simply the set S consisted only on take the set S consisted of Archimedean absolute values. So, and this immediately, of course, proves the theorem. I already erased it. Doesn't matter. Good. No, any gamma, just, yes. But you can always plunge it into S units, yes. You can always plunge it. Do some abstract nonsense. So let X as usual let X be a non-singular projective curve over number field K. Let little x be a non-constant function on K. Now, how we can state a theorem of Siegel? It turns out that theorem of Siegel can be stated as a necessary and sufficient statement. It's equivalence of two conditions. Well, of course, Siegel proved it only in the simplest possible case about integral points on. So probably, well, one more. Let me recall one more definition, and let me recall that we denoted by x of x OS. So S, finite set, subset in MK. And this is just all the points, all the k-rational points for which the coordinates is coordinate. So S integral points with respect to the coordinate x. And now theorem of Siegel, who he proved, I think, only in the case when OS is just OK, just there's a ring of algebraic integers, and the PID equations were developed by Mallers and by Lenk, but the ideas are the same, so I call it theorem of Ziegel. So the following two conditions are equivalent. First, X is of genus 0, or X has at least 3 poles. And second, this set O S prime is finite. S prime is finite for any finite extension K prime over K and any finite set S prime in M K prime. So actually, of course, yes, theorem of Ziegel, the main contents of theorem of Ziegel says that this implies that this set with OS is finite. But of course, then replacing K by K prime and S by S prime will obtain this. So the non-trivial part of the theorem of Ziegel is that 1 implies 2. But why I need here consider all of them? Because I want equivalence. In general, it is possible that one is not satisfied, but still this set, if we consider this set OS, is finite. But the equivalence statement tells that by extending either the field or the set of exceptional places, we can always, if this is not satisfied, by extending the guys, we can always achieve infinity here. So this is, so for instance, example, that if we consider the curve, so x squared plus y squared equal to 1, of course, this equation, or just let's say equation, has finitely many solutions in Z. Of course, it's clear, right? But if we take, it has infinitely many solutions. In the ring Z of I 1/2, which is a ring of S integers of the Gaussian field. Already in this ring, you can easily see that there are infinitely many solutions. I'm not sure about Z 1/2. I think there's still finitely many. I'm not sure. And similarly, theorem of Faltings can be also stated as an equivalent statement. The following are equivalent. One, g of x is at least 2 into x of k prime finite for any finite extension K prime over K. You may notice a feature of these two theorems. The first condition here is purely geometric. It has no arithmetic in it. Here or here, it's a condition which tells something about the geometry of the curve or of the function of the coordinate. So how many poles, but it's pure algebraic geometry, can be expressed as a curve of C, say. And the second condition is arithmetic. So certain geometry is equivalent to arithmetic. It's a sort of general principle. But when you speak on geometric condition here, then arithmetic is of kind of absolute. So true for all, guys. And similarly here. And now, let us speak about effective aspect. So, of course, Ziegel's theorem and Falsing's theorem are non-effective in this form. And currently, there doesn't seem to exist any method for proving full effective versions of any of this theorem. Now, let us say that Ziegel's theorem is effective for a curve, for a certain curve x, or let us say for a couple capital X, small x. Is effective for the couple capital X, small x, if well, there exists, there is a function, an explicit, let us say, I don't want here to give a precise mathematical definition, I just say it intuitively, but will be clear what I mean. What is an explicit function? A function that we can write down as a formula. There is an explicit function f, say, of two variables, d, and, well, I don't know how to know the other variable. I wanted to use letter. Okay, let us use a small letter p. Good? It's small p. Good. F of dp, such that for any k prime and s prime as above, and for any point p, which is s prime integral, have the height of this point P is bounded by f of the discriminant of the field K and little p of s, where little p of s is the maximal prime number below the places from S. Good? So we can S prime. So we can bound effectively all these sets. So in this case, we say that Ziegel's theorem is effective. Good? And one similarly say Falsing's theorem is effective. Effective and etc. Similarly, even easier to define what's Falsing's theorem is effective. For a particular curve, so the function f must depend on the couple, capital X, small f, x. Good? It again depends explicitly. And now, what I must say, that, at least to the best of my knowledge, and I think that in this case you can trust my knowledge, Falking's theorem is not known to be effective for a single curve. For some curves, we can bound points over certain fields, say over Q. In quite many cases, we know that there is no, on the Fermat curve, there are no non-trivial rational points or so. Some quite non-trivial results. But there is not a single example of a curve for where we can bound rational points over every field, if bound effectively. So Falking's theorem and so is not known to be effective for a single curve. On the contrary, Ziggy's theorem, and well, I think that at our present knowledge, it seems to be totally hopeless to, well, if one effective case of Falking's theorem in this form is discovered, it would be a great achievement. But I'm afraid that to discover one case, well, even there are some speculations by Shapiro, some other people, that showing that if we find one case, then at least in some strong sense, then we have everything. So
you mean to say there is no example where xk1 is empty for every k prime?
Sorry? There is no example where xk prime can be finitely, can be, which set?
There's no rational solution in q bar. You don't have
No. It is, you always, on every curve for sufficiently big k bar, you find a rational k bar rational, no, k prime rational point.
So, okay. You want some way a functional, some parametric way of bounding the
Bounding solutions only points bounding explicitly in terms of the fields.
I see.
And there is no way. So we don't know a single example of a curve where it is done. Of a curve of genus 2 or more where it is done. We don't know a single example. We know that this set is finite. We can bound its cardinality. This is doable. We cannot bound its size. So it is, this, I think, is a problem that belongs to subsequent generations. Well, of course, it follows from ABC, for instance, easily. That can be done. But ABC is, yes, well, let's wait. On the contrary, for Ziggy's theorem, we know certain effective cases. Many effective cases of Ziggy's theorem are known. And what I claim that all these cases, all effective cases of Ziggy's theorem, and by effective I mean exactly effective in this sense, so that you can bound effectively for any ring of S integers in any field. All of them can be done by Baker's method, and all of them are special cases of one general theorem, or no, not special cases, but either special cases of the theorem or can be deduced from the theorem by applying just covering trick and Chevalier-Weil principle. And let me now state this theorem. All that I know, let us be, but I say I know just to be cautious, but I don't really think that there is something that I do not know.
But in this statement, 24 is 1 and 2.
Yes.
To prove the second one is effective, there is no geometry repercussion, right? Should be like effective versus another two, right? There is no way. There is no way of linking it to geometry, right?
No, but just now I will state a theorem where there is a geometric condition gives you effective version of this, but only in one direction. We will not show that if this is effective, then we have this geometric condition. Yes, but follow from the following theorem. So let me state the theorem. So I use same setup, capital X, small x, and so on. Good? So assume the following condition is satisfied. Well, I call this condition B, but it is not what you think it is. B is for Baker. Because it's exactly the condition of applicability of Baker's method. So in the setup above, so we have x and x as above. Now assume condition B, that there exist two independent, non-proportional, let's say, principal divisors on x of k, supported at the poles of x. So x is a rational function. It has some finite set of poles, right? And the condition is that we can take a linear combination of these poles, which will be a principal divisor. Then we take another linear combination of these poles, which again will be a principal divisor. And these combinations are distinct, and they are not proportional combinations. So this is the condition. In other words, we can find two functions, essentially distinct two sort of units of the ring of integral closure of the polynomial ring generated by x. Two essential multiplicatively independent modular constants units. So this condition. Then, so it's again a geometric condition, slightly more complicated that of course, the condition in the initial Ziegel's theorem, but it is a geometric condition, purely geometric condition. Then Ziegel's theorem is effective in this sense for the couple X. And I claim that all effective, non-effective cases of Ziegel's theorem are either just special cases of the theorem or can be obtained by applying the covering technique to the theorem. So we take our curve, we take some étale covering, and on the covering curve, the assumption of the theorem is satisfied. Well, so let me prove the theorem. It is very easy. It's an easy theorem. So the only non-trivial part is Baker here. So let me write remark. B is for Baker. So one can also ask whether this condition itself can be effectively verified. This is not a completely trivial question. Say we have some finite set of points on a curve. Well, it basically reduces to the following problem. Are these points linearly dependent on the Jacobian of this curve? And whether this is a decidable problem or not, they decide whether the points are linearly dependent on the Jacobian. It's not very difficult, it's not completely trivial, but neither it's very difficult to show that if the points is defined over some number field, then it is a decidable problem. There was some note by David Masser explaining how it all can be decided. I'm not going into this because in all applications it will be pretty clear what are these divisors. So is decidable. Follows now proof. So let us let P be an integral point. So we may extend the base field K such that all poles of X are over K. Now, let P be in then the only guides which contribute to the height of X of P are those from S, and this means that there exists V in S such that log so dV over D log X of P, V is bounded by 1 over S height of X of P. So X of P V is big. Good. And now let's fix this V. This will be the V where we will apply Baker. Then X of P V-edically big, then by principles so that X must be close to a pole, P must be close to some pole of X. So there exists a pole Q of x. So I'm always do, you see, of course, if I were an accurate lecturer, I will always make, always make, point P as fixed and Q as varying, or vice versa. But since I am ad hoc lecturer, sometimes P is varying, Q is fixed. Sometimes Q is varying, P is fixed. Here, Q is fixed and P is varying. So sorry. I hope it doesn't bring too much discomfort. Such that the v-adic distance, whatever we defined it, is greater or equal than x of p, v, or some constant depending on v. And here 1 over E, where E is the order of the pole. Minus order of x at Q. I already don't remember. I put here order or I put here new. Maybe I put new. Doesn't matter. Or this implies that rho v of Q P is bounded from below to minus E, say some epsilon height x at P. Well, let us add 1 just to avoid stupid. Okay, where epsilon is better. Well, not here we put epsilon. Here we put some constant again. See what. Well, why say minus? E, so some constant e to epsilon height x of p. So we have that this, no, this is small, yes, minus epsilon, yes. So the distance is very small, like this, where epsilon is some positive number, which does not depend on p, but depends only on this data. So we can write it down, say epsilon is equal to 1 over E, 1 over S, and here d over dv, like this, something like this. Now we use condition B. So condition B says that there are 2 principal divisors, which means that if we take away our point Q, we still can find 1 principal divisor, 1 non-trivial principal divisor. So there is a non-trivial principal divisor supported, so this condition B implies that there is a non-trivial principal divisor supported at poles of X distinct from Q. And in other words, there exists a function well, since all of the poles are on K, so the function is also can be defined as a function over K, such that Z, the principal divisor of Z is supported on poles of X, and Z of K, Z of Q is not 0 and not infinity. And of course, we may assume that it is 1. Good. Now, what we know, what it means supported. It means that Z is integral over the ring of integers K of X. And same for Z minus 1, because poles and zeros, right? And now, by extending S, we may assume that Z and Z minus 1 are integral over OS of X, right? Which means that both Z of P, Z of P minus 1 are in OS. So Z of P is OS unit. Which is a finitely generated group, right? On the other hand, Z of P minus Z of Q is veridically what? It's bounded by some constant rho veridic distance of Q and P. And this is 1. So we obtain that Z of P minus 1 is bounded by this. And by the quasi-equivalence of heights, instead of hx, we can put h with respect to z, right? So with some other epsilon prime. Good. Because this is, well, I said small, well, of course, small. Small, yes, small distance, yes, not large distance. Epsilon prime hz of p, which is h of z of p, right? On the other hand, what Baker tells us, Baker in the modified form that I stated, he tells that z of p is 1, or z of p minus 1, so veridically, is at least E2 minus some constant. Well, let us put it just to avoid putting h the modified height. I put just normal height, but I allow here some constant, h log h z of p. And comparing these two inequalities, we see that we're done. And when it is 1, then there are only finitely many points, and again, we can easily bound them. So totally trivial argument, and basically it repeats what we did with 2A equation, but in slightly more general situation, right? Well, what was in the case of 2A equation, let me not erase the statement. first of all, remember that we found some root. So we had alpha 1, alpha n roots. And they correspond, roots exactly correspond to the poles of x, to the points at infinity. So they correspond, so we have exactly n poles of x. Of x, or of y, whatever. Now, the condition that x over y close to, say, alpha 1 is exactly selecting the nearest pole. Now, which are the principal divisors? Are those given by principal divisors supported on poles are exactly the divisors x minus alpha I y. So the divisors like this. It's clearly that this function, poles of this function are poles of x and y and are the same poles of x and y. But zeros of this function are also poles of x and y, because we multiply this function by similar guys, we obtain a constant. So zeros of this function are among the poles of other guys like this. So again, poles of x and y, right? And z will be exactly the guy that we used, x minus alpha 2y, x minus alpha 3y, well, correctly normalized. So it was alpha 1 minus alpha 3, alpha 1 minus alpha 2. So absolutely same argument. Sorry? Yes, and here we exactly need n degree equal to 3. So because we have, if we take all the n divisors, then they will be dependent. If we want independent, we take n minus 1 of them. And this means to have at least 2, we need degree at least 3. Yes. So what is, so this is just a generalization of this argument. But, well, to claim that this statement implies everything we know, and well, after the break, I will show you some examples how it applies to